Welcome to the mini lecture series on the Professor's DuBois channel. This is Professor Corey, and today we're going to continue with the second lecture from Chapter 13, which focuses on chemical mixtures. Previously, we discussed concentration units, and we'll apply these soon, but first we need to examine the process of making a solution. You'll see some words like solvation, and solvation is just dissolving a solute in a solvent. If water is the solvent, which it often is, you might see the word hydration, which is the same thing as solvation, but it implies that we're using water. We have the like dissolves like rule of thumb we can use for using polarity to decide if something may or may not dissolve. Polar solvents will tend to dissolve polar solutes. We'll talk more about that later. And if we're just looking at liquids, you might see this term miscible. So miscible is kind of like soluble, but for liquids. So if we had a solid dissolve, we'd say that the solid was soluble. But if we have two liquids that mix, we use the term miscible. So immiscible, oil and water. Those two do not mix very well. So looking at the solvation process, we have here, we're representing the sodium chloride crystal. And you can see that there's energy required to break apart those ions, forming those ionic bonds. But there's energy released when we form these ion dipole intermolecular forces around the ions. You can see those on the right-hand side. Notice how the water is arranging itself around the ions. So the water has a partial negative charge. Water has a dipole, and you can see by the arrangement where the partial negative is because the opposite charges will attract one another. So if we compare the bonds broken, like in our previous example, we had hydrogen bonds within the water, so we have to disrupt those hydrogen bonds. We also have to break those ionic bonds between the ions. So this requires energy, breaking these bonds. There's a positive delta H, positive enthalpy involved with this, but when we form bonds, we release energy. So we were forming these ion dipole forces, which release energy. And we can determine the enthalpy of dissolution by, it's a little bit simplified, but if we take the bonds broken minus the bonds formed, we can get an enthalpy value for the dissolution. So if the value is positive, it just means that it took more energy to break the bonds than what evolved when the new ones were formed. And the opposite's true if the delta H value is negative, or if it's exothermic. That just means that there was less energy required to break the bonds than the amount of energy that was given off when the new bonds were formed. So there's a lot going on here. In the case of the sodium chloride, we had those ionic bonds, and they're really, really strong. So it would require a lot of energy. Hydrogen bonding, that's strong intermolecular force, that needed to be broken too. But we form these ion dipole intermolecular forces, which are, pretty darn strong as well. But it gets complicated because remember the Coulomb's law, these forces are dependent on charge and distance. So there's a charge and size component as well. So we can't just say with certainty that, dissolving a salt is always exothermic or is always endothermic. What we can say is that nature favors lower energy states. So if something goes to a lower energy state, it gives off energy, or it's exothermic. So with things tending to be exothermic, you would think that, okay, if something dissolves, it must be exothermic. But that's not true either. And a good example is the cold pack for the injuries. And what we're doing with the cold pack is we're dissolving ammonium nitrate in water. And this actually has a positive delta H, which is not favored by nature. So there's another component here, and that's entropy. So entropy is the measure of disorder in a system, and nature favors an increase in entropy. you're going to see this delta S, and that's the change in the entropy. They're using S for entropy. So we can think about dissolving in terms of freedom of motion. So if we have a solid, that doesn't have much freedom. A solid's very constrained, but when we dissolve it in a liquid, now we have more freedom of motion. This would be favored by entropy. Now, dissolving a gas in a liquid, that's the opposite. So a gas has lots of freedom, but when we constrain it within a liquid, that's going to have a negative delta S. So if we looked at the just vaporization of water in terms of entropy and enthalpy, we could say, well, it takes energy. We have to put in energy to put the liquid into the gas phase, and that's going to have a positive delta H. So enthalpy is not favored, but going from the liquid to the gas state does increase entropy, which is favored. We can look at this predicting solubility chart and we can ask ourselves, okay, is our dissolution enthalpy favored? And that means, does it have a negative delta H? That would be favored by enthalpy. Well, if it does, and it has a positive delta S, or a positive entropy, we can say with certainty that the solute will be soluble. Now, if it isn't enthalpy favored and it's not entropy favored, this is the other end of this chart, then it's not going to be soluble. But when we're favored for one and not the other, then we have a temperature component. And if we look at our vaporization, we said that that was not enthalpy favored. So, but it was entropy favored. And if we follow our little flow chart here, so we're not enthalpy favored, but we are entropy favored, we can say vaporization will occur at higher temperature, and this makes sense. When we have a liquid dissolving in a liquid, the same thing happens. We've got water here and methanol, both have hydrogen bonding. We have to break these hydrogen bonds, and we form new hydrogen bonds with the mixed liquids. Just bringing back like dissolves like, nonpolar solutes tend to dissolve in nonpolar solvents, polar solutes in polar solvents. So this is a good rule of thumb. We can use this to make predictions about solubility if we don't have the entropy or enthalpy values. Some things to look for are what we call functional groups, or groups on molecules. And if we see OHs or NHs, we say this is hydrophilic. And this is polar, so it's very likely that these will be soluble in a polar solvent or in water. Hydrophobic, these are long hydrocarbon groups. Now notice at the bottom we've got two examples. One of them is just a pure hydrocarbon, and we can say with certainty that this is not going to be soluble in water. But the other example does have an OH, and this is hydrophilic because of the OH, but it also has that long carbon chain. So we don't know with certainty if this will be soluble or not. This gets a little bit tricky, but what we could ask is we could have a methanol, a CH3OH, and then an ethanol, and a propanol, and a butanol, and then we could ask which would be more likely to be soluble in water, in which case the shorter the carbon chain, that's going to be more hydrophilic or more able to dissolve in water. So just something kind of interesting, if we look at ionic compounds, we've got a metal and a non-metal. They're very, very polar. They're so polar that the metal just gives away the electron to the non-metal. So you would think that these would always be soluble, like dissolves like. And if you remember back in Chem 111, we had our solubility chart for aqueous solutions, and not all ionic compounds were soluble. And this comes down to a thing called a hydration number. And the hydration number is the number of water molecules that are constrained by the ion. So if we went back to the image with the sodium chloride, we had water molecules that were around each of those ions. So if we have a small radius and a high charge, we have a greater hydration number. And this is going to be entropy disfavored for dissolution. So again, a lot going on here. It's, like dissolves like is a good rule of thumb. That's a good place to start, but it doesn't always work because we have our entropy and our enthalpy components that also play a big part in whether or not something will dissolve. So this is really the theory of something dissolving, and next we're going to get into a little more detail. So stay tuned for our next mini lecture on the Professor's DuBois channel.